Greetings, physics enthusiasts. Welcome back. Here we are, AP Physics 2, still Unit 1, Lesson 2. And today I want to talk to you about density and then pressure. Density and pressure. So when we have stuff, that stuff occupies space. And if we measure both of those things together, we're going to want to know, there we go. We're going to want to know how much stuff is in there. And I want to know how much space it takes up. And that's what density is. Density is defined as how much stuff, so the mass of this block, divided by how much space it takes, the length times the width times the height, or the volume. Density is a measure of how much stuff divided by how much space the stuff takes up. Now, I know you learned that in junior high before, and so that's why I went over it really fast. But this is not going to be mind-blowing. I could rewrite this so that there's no fractions, and I could have density times volume equals mass. Again, not mind-blowing. So we often replace mass in equations with density times volume. And then the only thing I'm going to say in addition to that is sometimes instead of capital D for density, we use the Greek letter rho, R-H-O, the Greek letter rho for density. Did I say for volume? So we use the Greek letter rho for density. We still use capital B for volume, and we still use M. So, for example, if I wanted to talk about the fact that Earth pulls this block down, I often label that arrow mg. That's how hard Earth pulls stuff down. But when we're talking about fluids, when we're talking about liquids and gases, instead of mg, I will often write rho vg. Rho v is m, and then g is still g. So we often say rho vg for mg when we are talking about fluids, solids, not so much solids, but liquids and gases. So anyway, there's a little intro to density, and that's all I got. We'll use this in an example problem in a few minutes. Now, pressure. Right now, I am being pushed on by air particles all around me. And that, is trying to squish me. I could talk about the air particles in my mouth pushing out on my cheeks, and I could increase the force they exert. And I don't really want to talk about how hard each air particle is pushing, but I do want to talk about that total force exerted. It's creating a funny little feeling here. Anyway, so when we're interested both in how hard all these things are pushing and the area on which that force is being exerted, then we talk about pressure. Pressure is defined as the total force, the sum of all the little forces being exerted by little things like air particles, divided by the area on which those forces are being exerted. And it just turns out that that is often a more useful way to talk about it. And definitely, I can talk about the pressure in this room is, I know the pressure in this room is about 101,300, really, newtons for each square meter. That's the pressure in this room. And of course, a Newton per square meter, I could also name that after some other dead scientist. I could call that 101,300 pascals. We tend not to do that when we're talking about just, the air exerting forces on walls in this room. We just want to say, it's just, room pressure. We just want this to be something not weird like 101,000. So we often call that 1 atmosphere. An ATM is an atmosphere. Different units for pressure. Of course, we know a Newton is a kilogram times meters per second squared. And if I divide that by square meters, kilograms times meters over second squared, and I divide that by square meters, this M cancels one of those. I could say this is also 101,300 kilograms over meters second squared. All of these are the pressure in the room. Sometimes when we're blowing up our bicycle tires or the tires in our car, we talk about pressure in pounds per square inch. I don't even know. Convert 1 atmosphere to pounds per square inch. I'm going to press pause for a second because a friend just walked into the room. A very important friend came by. And you'll notice that I looked up that question and it's 14.7 pounds per square inch. That is atmospheric pressure. So there's lots of different units we can use to express pressure. Another one that's really weird, 760 is atmospheric pressure. 760 what? Millimeters of mercury, mmHg. And we will talk about that later in a class activity. Why on earth millimeters of mercury, that distance, 760 millimeters, about almost a meter, why that distance is a measure of pressure as well. But what you need to know is that pressure is force divided by area. And I think we've talked about that sufficiently here. So now what I want to do is I want to talk to you about pressure variation with depth. Pressure variation with depth. I'm going to turn my paper this way because it feels like it's more authentic to talk about depth if my paper is tall. So pressure variation with depth. What does that mean? Variation with depth. Maybe you have done some scuba diving, lucky you. Maybe you have done some snorkeling, or maybe you've just swum around in the pool and you've noticed that you dive into the pool and when you go deeper, it kind of hurts your ears. And if you're going really deep, like people with scuba tanks do, you have to make sure not to change your depth very fast because it's hard for your body to catch up with that pressure change. Maybe you've driven down Highway 2 and you've noticed as you get down toward Glendale, you have to pop your ears because the pressure has changed. The pressure is greater down in Glendale than it is up here in La Crescenta. Maybe you've driven up and down Briggs Avenue and as you go up Briggs, you're changing your elevation pretty fast and the pressure is changing. And when that happens, you're gonna have to pop your ears to help that pressure equalize. It also happens if you're on a plane when you're taking off and landing. So anyway, those are some physical examples that you felt in your body about pressure variation with depth. And I want to do some math with that because nothing is better than math. So let's say we're underwater and I want to talk about the pressure here being different from the pressure here. We could call the pressure here P1 and the pressure here P2. I know as I go down, the pressure increases. As I go up, the pressure decreases. And I want to figure out how much the pressure increases or decreases as I have this height change. So we'll call this vertical distance H, the height. And what I'm going to do in order to think about this is I'm going to draw a cylinder. So there's lots and lots and lots of water everywhere. I'm just going to look at this one little specific cylinder of water, the top of which corresponds to a pressure P1 and the bottom of which corresponds to a pressure P2. One thing you might wonder about this cylinder of water is why it doesn't fall. Thank you. And so why does this cylinder of water not fall? You know, this cylinder that is my pen, it falls when I let go. Why isn't this falling? Well, what is Earth pulling this cylinder of water down? Yes. So why is it not falling? Because somebody's pushing it up. It turns out that the water underneath is pushing it up. And you might be saying, but wait, isn't the water on top pushing it down? Yes, the water on top is pushing it down. But you'll notice that I made these arrows long, that was on purpose, and these arrows short because the pressure is greater down here and the pressure is less up here. And therefore, every little water particle that bangs into the cylinder of water is pushing harder than all the water particles here. And then, of course, Earth is pulling the water down with a force mg. So if this cylinder is not going to sink to the bottom of the ocean, it must be because the net force is 0. These down forces plus this down force must add up to the same size as these up forces. So why does the cylinder not fall? Because these guys are pushing up to counteract all the downward forces. So my total net force, the sum of all the forces, equals 0. So let's do a little bit of math and see how that works out. I'm going to say that this, so the pressure up here is P1, and there's these little forces. So what I'm going to say is the sum of all these arrows is little f. And if I divide those by this cross-sectional area A, force divided by area, that equals P1. I could do the same thing here. I've drawn a cylinder because I wanted this cross-sectional area at the bottom to be the same as this cross-sectional area at the top. But the sum of all these arrows is not lowercase f, it's capital F. This is a much bigger force down here. So this force divided by the same area gives me P2, this greater pressure. Do you see it? And so now what I'm going to do is I'm going to make the sum of the forces 0. So my positive force, F, instead of F, I'm going to write P2A. P2A. Do you see that F equals P2A? I love it when people walk by and wave at me, but they're very nice not to have walked in. Okay. So F is the upward force, and it equals P2A. The downward force here is smaller. It's P1A minus P1A. I said minus because it's a negative force. It points down. And then I also have to remember to subtract mg, and that total force is going to equal 0. Does that equation make sense to you? I've got this downward force, they're both negative. This upward force, it's positive. The big upward force is P2A. The little downward force here is P1A. And then of course this is mg. All that makes sense? I'm hoping the answer is yes. Now, I'm going to make a substitution. Instead of mg, where's that piece of paper? Instead of mg, I'm going to write rho vg. Okay, so I'm going to do that right now. So I'm going to say P2A minus P1A minus rho vg equals 0. mg became rho vg. And then instead of volume, what is the volume of this cylinder? It's the cross-sectional area A times the height h. So I'm going to have P2A minus P1A minus rho v. Instead of v, I'm going to say cross-sectional area times H. This area times this height is the volume times G equals 0. And what that allows me to do you see that A is in every term? So I can give me a different color. So I can cross out the A's because they're in every term. And I get P2 minus P1 equals, I'm going to move this over here, rho GH. And that is the equation I'm looking for. It's a very exciting equation. It says the difference in pressure between these two places, difference in pressure, P2 minus T1, that's delta P, delta pressure equals rho GH. So the change in pressure is greater if it is something denser. There's a bigger pressure change when I go 10 feet down in the water than when I go 10 feet down in the air. When I walk up to Miss Harris's classroom, I don't have to pop my ears. But if I were to swim that depth, that would be a much greater change in pressure because there's a greater density in water than there is air. G is just our proportionality constant having to do with, here on Earth. And then H, greater distance, corresponds to greater pressure difference. So this is a really, really, really important pressure variation with depth equation. I'm just looking at how much time I have. I'll have plenty of time to talk about what I want to talk about. So let's rewrite that. P2 minus P1 delta P is rho GH. Sometimes, like in the book, it's written as P2 equals P1 plus rho GH. I know that is not exciting. I moved this over to the other side. So they're saying whatever your original pressure is, add rho GH, that gives you your final pressure. Ta-da! Now, sometimes this part right here, I don't know why, it doesn't seem important to me. This part right here, the change in pressure, right? We said the change in pressure was rho GH. The change in pressure, pardon me, is called gauge pressure. I think what happens, you can correct me if you know about this and I'm wrong, but I think what happens is when you're scuba diving, you have your little pressure meter because it's really important. You can, if you don't pay attention to the pressure, you can get injured. So your pressure meter doesn't say something like 101,300. That's not helpful. What it says when you're sitting in the boat is 0. So your little pressure meter on your watch, it just says 0. And that's how much the pressure has changed. Hasn't changed any yet. And what you care about as a scuba diver is not what the pressure is. What you care about is how much the pressure has changed. So your gauge pressure that you wear on your wrist is going to tell you how much the pressure has changed. So just realize that these phrases are synonymous. Change in pressure is called gauge pressure. This is often called, it's the pressure that actually is, it's called the absolute pressure. And I have seen several times on the AP exam where super simple equation and you do all your work and they ask you, hey, what was the gauge pressure? And you're like, I don't know, which one were you trying? Gauge pressure, absolute pressure. So sometimes they want to know if you have paid attention to that vocabulary. Sometimes this is also called hydrostatic pressure. And the idea is that it's a fluid, hydro, and the fluid isn't moving. The water, you're not doing this in a river, you're doing it in the ocean where the water is generally at rest. We can assume it's at rest. Later on in this chapter, we're going to talk about when the fluid is flowing, and then that makes things different. So we're not taking into account fluid flow here. Hydrostatic fluid, it ain't moving. All right, I'm just looking at my notes to to see what other things I need to be sure I have talked about. Okay, there's only one more thing here. Pressure variation with depth. The pressure depends on the depth. So there are some really fun examples that we can deal with here. And sometimes we have a fun device where there's a tube and I put a little piston in here. And so the piston allows me to push down and compress the fluid in here. And then the fluid is going to rise in this other chamber. But you'll notice that this chamber is wide and this chamber is thin. So if I push down here, just a small amount, the piston on the other side over here is going to rise a much greater distance. And that's just really fun. I can push down a small distance here and then whoosh, this goes up a great distance. And that allows for some fun things. But in this kind of situation, what we have to realize is that at a given depth, it doesn't matter if it's on the left side or if it's on the right side, if it's in the wide chamber or if it's in the skinny chamber, the pressure at a given depth is the same. So at a given depth, the pressure is the same. I can push down here and it doesn't, and increase the pressure inside. If it increases the pressure here, it'll also increase the pressure here. So at a given depth, the pressure is the same everywhere at that depth. And that's called Pascal's principle. Pascal's principle. The same Pascal after whom we named the unit for pressure. Remember I said PA Pascal, same guy. This guy, Pascal, also wrote a book called The Pensée. Very fun book if you ever want to read it. Anyway, so Pascal's principle, if I know the pressure at the depth here, if I move somewhere else, it's the same depth, same pressure. All right, and that is all I have for you today. We're getting through this stuff. I hope you have a wonderful day. Thank you so much for your attention. Don't break the laws of physics.